Well, the first type of problem we want to talk about is simply supported beams. Simply supported beams have a pin and a roller. So here's our beam, and here's a pin and a roller. And this is extremely common in terms of the type of structures that we'll not only analyze in this class, but what we'll see in real life. And it also is one of the easiest to get started on. So first thing we want to do is draw a free body diagram. And I like to draw a free body diagram in the pretty much the same shape that the picture is in. This is in our idealized model. But let's draw the applied forces. Now, you can draw this 500 pounds in here, or you can just go straight to the components. And I'll try to do that. Because this is a 500-pound force, this is the 4/5 component going down, so I know that that is going to be 400. And this will be the 3/5 component, so that'll be 300. And let's also apply the moment over there of 600. Now let's draw the supports. B is a roller, so I know that it only can support force in the y direction. A is a pin, so it has an AY and an AX. Now I've drawn it to the left here. Why did I do that? Well, because it's obvious to me that this force is pushing it this direction, so I know that the reaction is going to go in this direction. And once you kind of get some skill here, you'll be able to do that by inspection many times. All right, let's write our equations. We only have 3 equations, so we're going to use them all. Sum of the forces in the x is equal to 0, so I have minus AX plus 300 equals 0. Those are the only forces in the x direction, so I've solved for the first component of our reaction is 300 pounds. All right. How about some of the moments? Let's try some of the moments about point A. And you can do them in any order, and again, with experience, you'll find out what gets you the answers the quickest. But I'm going to say some of the moments equal to 0 about point A. And again, you can sum the moments about any point. This one I'm summing the moments about because I want to find out what the reaction at B is, and I can do that with one equation, as we'll find out. All right, let's see what the moments about point A is. I have this 400 times this lever arm, By times this lever arm, and then I got that applied couple over there. So let's go ahead and put all those in. Minus 400 times 5 plus By times 10. And then negative 600. 600 is going in the clockwise direction. And I can solve that for By. And that's equal to 260 pounds. And that gives me the second unknown. And I just want to point out here that the 600 is a free vector. It can be applied any place along the beam. It happens to be applied out here at 15, but it could be applied any place. So when you put it into the calculation, the 600 stands alone. Don't multiply it by 15 any place in the calculation. And now I can sum the forces in the y direction. I'll go ahead and push that up just a little bit. Sum of the forces in the y. What forces do I have in the y? AY minus 400 plus By equals 0. I've already solved for By, so now I can solve for AY is equal to 140 pounds. Again, this isn't a very difficult problem. But it is indicative of the process, and the process I want to go through is very, very simple, but very, very important. Draw the free body diagram. Isolate everything from its surroundings. Do not draw the pin, do not draw the roller, only draw the forces that are acting on your beam. And then we have those two forces from the pin and that force from the roller. That's the way to do the free body diagram. Then write the forces. Make sure that you write an equation that to start off with that is equal to 0. Sum of the forces in the x is equal to 0. Then right underneath it, you write those forces equal 0. This is extremely important. This is very logical the way you do it. sum of the moments equals 0, and then write all the moments equals 0. Sum of the forces in the y, and if you follow that process, then you won't get lost, and your communication should be pretty clear. Well, the next one we want to analyze here is this L-shaped bracket, and we want to find the reactions at B and A. Well, it's pretty clear that this is a pin because it's got a pin. This one, it may not be obvious that it's a roller, but it's probably a frictionless surface, and I think the problem in the textbook probably would say consider B to be a frictionless surface. So we're going to do that. Let's draw a free body diagram. So I'm going to draw it over here, and like this. Oops, that was kind of bad. All right, I'm going to apply a 8-pound force here. I know that this is a pin, so I'll say that that is AX, and I'll say AY. Now what's that B? I'm going to assume that that is going up. And the reason I can assume that is because if it is a roller, I know that it can't pull down. The only thing it can do is push up. So I know that the force has to be going up in that direction. Alright, so now we've got our free body diagram. Let's do our forces. Some of the forces in the X. Alright, so I've got minus 8 plus AX equals 0. So we've got one answer. AX is equal to 8 pounds. Alright, how about a moment equation? Let's do some of the moments about A. I'll do that one over here. Some of the moments about A is equal to 0. And if I do that, I've got 8. And here is my lever arm for the 8. 8 times this lever arm, which looks like 1.5. And that's going positive because it's going in that direction. Then I got that B, and that's going to be in the negative direction. You can see that it's trying to rotate it going in this direction, and it has this lever arm of 2. And so BY is equal to 6 pounds. And then some of the forces in the Y. So here I have BY plus AY. Now I've already solved for BY, so it gives me AY is equal to negative 6. Now, is that okay? Yes, that is okay. When I drew the free body diagram, I didn't know which direction it was going to go, so I assumed that it was up like that. But it's actually going down. It's actually pulling down like that. And when I solve it, I get a negative answer. This is a perfectly acceptable way of displaying your answer. You don't have to go back and change this to a positive or anything like that. What it is important is that the answers agree with your picture. In other words, if you draw it as a positive force, when you use it in an equation, it's a positive force. If you draw this one as a positive force, then it needs to be a positive in the equation. When you resolve it and you get a negative answer, that is okay. Well, this is just another look at negative forces and positive forces. Just want you to make sure that you understand that the picture, the free body diagram, must agree with your equations. For example, let's say that we have a pin and a roller, and we're going to apply a force of 10. And let's say that dimensions 1 and that dimensions 2. Let's draw a free body diagram. Got 10. And I'm going to have a pin here, so I have AX and AY. And we'll call that point A, this point B. And let's put over here BY. Okay, if I sum the moments about point A, what have I got? I got this negative 10 times 1 plus BY times 2 equals 0. I can solve that for BY is equal to 5. And that's a good positive answer, agrees with my arrow. However, now the sum of the forces in the Y is equal to 0, so I got AY plus BY equals 0, and you can solve this for AY is equal to negative 5. And again, is that acceptable? Yes, it is acceptable. In fact, it's very proper. But it just makes sure that when you draw your forces in the picture as a positive, if you have it going up, then it must be a positive in the equation. Well, the next one I want to do with you is just a little more complicated. It is still a simply supported beam, has a pin and a roller. It's obviously a two-dimensional beam, which is just fine. But let's see if we can find the reactions. Now, what I'm going to do is assume that the shape is thin. The reason I'm going to do that is so that if I apply a force here, it doesn't have any additional weirdness about the lever arm because if this had some thickness. So I'm going to assume it's thin. You can watch as we do this. Let's first draw the free body diagram. Okay, I'm going to have a couple here of 800. And let's draw the components of the applied force here. I know there's a force in that direction and here. And this will be the 12/13 component of 390. And this will be the 5/13 component of 390. Alright, the roller over here is going to be, the contact force is going to be like that, but it actually has two components. It has a component here and a component here. If this is 30 degrees, the angle that this makes with the horizontal, that makes this 30 degrees. So I'm going to put the two components here. I'm going to say that this is A cos 30 and this is A sine 30. Alright, the last two components we're going to put on there is the pin, and I'll say that that is going to be a by and a bx. Again, I don't know for sure if it's going in this direction, but I'm going to guess that it's going that way, and we'll see if I guessed correctly. Alright, three equations. Let's sum the forces in the x. So here I have positive A sine 30 minus 5/13 times 390 minus bx equals 0. Now I have two unknowns there, so I can't resolve that. So let's sum the forces in the y, see what we can get. Here I have positive A cos 30 negative 12/13 times 390 plus by. Now again, I introduced yet another variable. I have bx over here and by. I'm still using my a, but now I have two equations, three unknowns. So let's try the last equation, which is a moment equation. Now here, where should I sum the moments? I'm going to sum the moments about point B, and I think you'll probably see why in a second. So sum of the moments about B equals 0. And what have I got? This force has this lever arm trying to go in this direction. This force has this lever arm here, which is trying to go in that direction. So let's go ahead and write those down. A sine 30 times 3, and that's negative, and then A cosine 30, and it has a lever arm of 8. Alright, what else do I have? I have this applied moment here, that torque, and I also have this component, or this couple I mean, and I also have this component with this lever arm. This component here, it goes through the point that I'm summing moments about, so there's no lever arm associated with that. So let's go ahead and add those two in. So I have plus 800 in the counterclockwise direction, plus 5/13 of 390, and its lever arm is 3, and that's all equal to 0. Alright, when you solve that, then you can get something you can start dealing with. I solved this for A is equal to 148.3 pounds when I did my algebra. Then I plug that into that equation and that into that equation, and I can solve for the other two components. So I have bx is equal to negative 75.85 and by is equal to 231.6 pounds. Now let's just check our answers and make sure we did it properly. But the by answer makes sense. It is going up, which sounds pretty good. The bx answer I thought was going negative. When I resolved it, I got a negative answer, which means it disagrees with my arrow, which means all along it was going in this direction. So again, it's not unacceptable. This is actually very acceptable to say I thought it was negative, but when I resolved it, I got a negative answer. And whenever you get a negative answer in your calculation, that means it disagrees with your arrow. It disagrees with your assumption. And again, we'll get used to this as we go forward.